Okay, so I think that should be fine. Let's see if this sounds good. Good. Does this sound good? Good. Does this sound good? Good. Okay, it does. Nice. All right, so today we're gonna carry on with our deep learning, and I think we left off here. Okay, interesting. That counts as seconds. That's pretty interesting. All right, so as we can see, we have 4 layers at the moment, which is the input layer, which is always the far left, the hidden layers, which are the layers in the middle, and the output layer, which is the layer to the right side. The design of the input and output layers in a network is often straightforward. For example, suppose we're trying to determine whether a handwritten image depicts as a 9 or not. An actual way to design network. I'm gonna change music here. That is not what I was expecting. I want to do some like lo-fi or whatever. Yeah, this is good. So they are pretty straightforward. An actual way to design the network is to include an intensities of the image pixels into the input neurons. If the image is 64 by 64 grayscale image, then we have the multiplications between those two numbers, which is equal to 4096. With the intensities scaled approximately between 0 and 1. The output layer will contain just a single neuron, with output values of less than 0.5 indicating the image is not a 9, and the value is greater, 0.5 indicating that the image is 9. So it's either smaller or greater in this case. When the design of the input and output layers of neural network is often straightforwarded, there can be quite an art. I actually want to kind of write this down because this gives you like a very basic idea on how it works. So I'm gonna do that. And this is an Ericsson bottle, I guess, as well. So you guys, if you guys wonder, I'm not sponsored, by the way. They just gave it to me. But yeah, so basically this tells us how to design an input layer, and then we have I'm actually gonna come back to this page probably, so it's page 15. I'll write this down later. Make a star or something, just so I know I can write it down. All right. So yeah, the design of the input layers in a network is often straightforward. For example, suppose we're trying to determine whether a handwritten image depicts a 9 or not. A natural way to design a network is to encode intensities of the image pixels into the input neurons. If the image is 64 by 64 grayscale image, then we have an amount of pixels which is 4096, but that is also equal to 64 times 64 input neurons, with the intensities scaled appropriately between 0 and 1. The output layer will contain just a single neuron, with output values of less than 0.5 indicating input image is not a 9, and the value is greater than 0.5 indicating that an input is 9. So it's like an greater or less classification. While this design of the input layer and output layers of neural network is often straightforward, there can be quite an art to design of the hidden layers. In particular, it's not possible to sum up the design process for the hidden layers. There are simple rules of thumb. Instead, neural networks researchers have developed many design heuristics for hidden layers, which help people to get behavior they wanted out of their nets. For example, such heuristics can be used to help determine how to trade off the number of hidden layers against the time required to train the network. We will meet several such designs heuristics later in this book. And up to now, we have been discussing neural networks where the output from one layer is used as an input to the next layer. Such networks are called feed-forward neural networks. So backpropagation is the opposite. This means there's no loops in the network. Information is always fed forward, never fed backwards. If we did have a loops, we would end up with a situation where the inputs to the sigmoid function depend on the output, and that would be hard to make sense of, so we don't allow such loops in this particular case, by the way. However, there are other modules of I'm just gonna turn the page here, of artificial intelligence or artificial networks, neural networks in which feedback loops are possible, and these models are called recurrent neural networks. I guess this is a link or something. No, okay. The idea of these modules is to have neurons switch fire for some limited duration of time before coming quiescent. That fire can stimulate other neurons, which may fire a little while later, also for a limited duration. That causes still more neurons to fire, and so over time we get a cascade of neurons firing. So it's basically a recurrent neural network. So it's basically firing itself, or the neurons are firing themselves together. Loops don't cause problems in such modules, since the neuron's output only affects its input at some later time, not instantaneously. Recurrent neural networks or neural nets have been less influential than feed-forward networks, in part because the learning algorithms for recurrent nets are, at least to date, less powerful, but recurrent networks are still extremely interesting. They are much closer in spirit to how our brains work and feed-forward networks. And it is possible that recurrent networks can solve important problems which can only be solved with great difficulty by feed-forward networks. However, to limit our scope in this book, we are going to concentrate on the more widely used feed-forward networks. Okay. A simple network to classify handwritten digits. Having defined neural networks, let's return to handwriting recognition. We can split the problem of recognizing handwritten digits into two sub-problems. First, we would like a way of breaking an image containing many digits into a sequence of separate images, each containing a single digit. For example, we would like to break 504192 into 6 separate images. Like this. And I think this paper is from someone that is Chinese, by the way, because these are Chinese symbols. We humans solve this segmentation problem with ease, but it's challenging for a computer program to correctly break up the images. Since once the image has been segmented, the program then needs to classify each individual digit. So for this instance, we would like our program to recognize the first digit above, which is the 5. We will focus on writing a program to solve the second problem, that is classifying individual digits. We do this because it turns out that segmentation problem is not that so difficult to solve once you have a good way of classifying individual digits. There are many approaches to solving the segmentation problem. One approach is to trial many different ways of segmenting the image using the individual digit classifier to score each trail segmentation. A trail segmentation gets a higher score if the individual digit classifier is confident of its classification in all segments, and a low score if the classifier is having a lot of trouble in one or more segments. So it's basically, the higher score means that we have a better general performance, and lower score means that we have a worse general performance. The idea is that if the classifier is having trouble somewhere, when it is probably having trouble because the segmentation has been chosen incorrectly, this idea and other variations can be used to solve the segmentation problem quite well. So instead of worrying about segmentation, we will concentrate on developing a neural network which can solve more interesting and difficult problem, namely recognizing individual handwritten digits. To recognize the individual digits, we will use a 3-layer neural network, which is basically looking like this. I'm gonna go back and paint this on my paper later. But for now, let's just carry on. So this is page 18. Figure. Page 18. So the input layer of the neural network for the network contains neurons encoding the values of the input pixels. As discussed in the next section, our training data from the network will consist of many 24 by 24 pixels images of scanned handwritten digits. And so the input layer contains 784, which is equal to 28 times 28 neurons. For simplicity, I've committed most of the 748 input neurons in the diagram above. Which is here by one. The input pixels was grayscaled with a value of 0.0 representing a white and a value of 1.0 representing a black, and the in-between values representing gradually darkening or shading of gray, which makes sense. The second layer of the network is a hidden layer. We denote the number of neurons in this hidden layer by n, and we will experiment with different values of n. For example, shown illustrates a small hidden layer containing just n, which is equal to 15 neurons, and this is probably this one here. The output layer of the network contains 10 neurons. If the first neuron fires, it has an output which is kind of equal to 1. Then we will indicate that the network thinks the digit is a 0. If the second neuron fires, then that we would indicate that the network thinks it's a 1, and so on. So it's basically, if this fires, it's a 0, this 1, and so on. Alright. You might wonder why we use 10 output neurons. After all, the goal of a network is to tell us which digit 0 to 9 corresponds to the input. Similarly, natural way of doing that is just to 4 output neurons treating the neuron as taking in a binary value, depending on whether the neuron's output is closer to 0 or 10 or 1. 4 neurons are enough to encode an answer, since 2 to the power 4 is equal to 16. is more than 10 possible values for the input digit. Why should our network use 10 neurons instead? Isn't that inefficient? The ultimate justification is empirical. We can try out both network designs, and it turns out that for this particular problem, the network with 10 output neurons learns to recognize digits better than the network with only 4 output neurons. But that leaves us wondering why using 10 output neurons works better exactly. Is there some heuristic that would tell us in advance that we should use 10 output encoding instead of the 4 output encoding? To understand why we do this, it is to help think about the neural network is doing from the first principles, considering first the case where we use 10 output neurons, so let's concentrate on the first output neuron, and then ones that's trying to decide whether or not the digit is a 0. It does this by weighing up evidence from the hidden layer of neurons. What are those hidden neurons doing? Well, just suppose for the sake of argument that the first neuron is a neuron in the hidden layer that detects whether or not an image like the following is present. Yeah, makes sense. It can do this by heavily weighting input pixels which overlap with the image, yeah, and only slightly weighting the other inputs in a similar way. Let's suppose for the sake of argument that the second, third, and fourth neurons in the hidden layer detects whether or not the following image are present. As you may have guessed, these 4 images together make up a 0 image that we saw in the line of digits shown earlier. Yeah. So if all 4 of these hidden neurons are firing, then we can conclude that the digit is a 0. Of course, that is not only sort of evidence we can use to conclude that the image was 0. We could legitimately get a 0 in many other ways, say through translations of the above image or slightly distortions. But it seems safe to say that at least in this case we would conclude that the input was a 0. Supposing the neural network functions in this way, we can give a plausible explanation for why it's better to have 10 outputs from the network rather than 4. If we had 4 outputs, then the first output neuron would be trying to decide what the most significant bit of the digit was. And there is no easy way to relate the most significant bit to simple shapes like those shown above, and it's hard to imagine that there's any good historical reason. The component shapes of the digits will be closely related to, say, the most significant bit in the output, which kind of makes sense. Now, with all that said, this is just a heuristic. Nothing says that the 3-layer neural network has to operate in a way I described, which makes sense because this is only hypothetical. With the hidden neurons detecting simple component shapes, I think the best way to actually kind of realize how this neural network works is to see how the neurons fires based on the sigmoid function, and then understand like a hidden pattern for this specific use case. Maybe a clever learning algorithm will find some assignment of weights that lets us use only 4 output neurons, but as a heuristic, the way of thinking I've described works pretty well and can save you a lot of time in designing good neural networks. I kind of disagree with this actually, because this is based on trial and error when it comes to seeing how neural networks behaves. So you first look at the first one and then you look at the second one and so on until you see like a pattern. So in large scale, this is actually super bad to do. But I guess it could be a good introduction for some people. So exercises. There's a way of determining the bitwise representation of a digit by adding an extra layer to the 3-layer network above. The extra layer converts the output from the previous layer into the binary representation, as illustrated in the figure below. Find a set of weights and biases for the new output layer. Assume the first 3 layers of neurons are such that the correct output in the 3rd layer and the old layer has activation at least 0.99 and incorrect outputs have activation less than 0.01. I wouldn't do this exercise because it's super hypothetical and doesn't really work with real neural networks. But you know, we could just like paste this whole thing into ChatGPT and see what it says, but I don't think it's gonna give us any answers because this is just too hypothetical. I see what you're referring to. Yeah, he understands that it is the book that we are trying, which is chapter 1. Yeah, problem relates. We have a 3-layer input, hidden output. Yeah, the 3rd layer, output layer, is set up for digit classification. Yeah, that makes sense. And then the correct digit neuron activation is 0.99, and incorrect digit neurons activation is 0.01. Now that we have added an extra layer in the output layer to convert one hot encoding into the bitwise binary representation of the digits, 4 bits to represent 0 to 9. The old output layer has 10 neurons, 1 per digit, which makes sense. And I think that is it's this one here. The new layer should have 4 neurons for the binary digits, right? So instead of having 10, we basically make this a hidden layer, I think, and then put 4 neurons here, and they should act as an output layer. Yeah. Yeah. So yeah, we have a binary sequence here. Least significant bits. Yeah, so this is not even using a sigmoid function, it's using euros. So this will actually not work at all. Whatever. Now that we have a design for our neural network, how can it learn to recognize digits? The first thing we will need is a dataset to learn from a so-called training dataset, and they use the MINIST dataset, which contains tens of thousands of scanned images of handwritten digits. Together with their correct classifications, MINIST name codes with from the fact that it is a modified subset of 2 datasets collected by NIST, which is the United States of National Institute of Standard and Technology. Here's a few images from the MINIST. MNIST, I think. As you can see, there are digits. These digits are in fact the same as shown at the beginning of the chapter. Yeah, it makes sense as a chance to recognize. Of course, when testing our network, we will ask it to recognize images which aren't in the training set. Now, the MINIST data comes in 2 parts. The part contains 60,000 images to use as a training data. These images are scanned handwriting samples from 250 people. Half of them were from whom were US Census Bureau employees, and half of them were high school students. The images of grayscale and 28 by 28 pixels in size. The second part of the MINIST dataset is 10,000 images to be used as a test data. Again, these are 28 by 28 grayscale images. We would use the test data to evaluate how well our neural network has learned to recognize digits. To make this a good test of performance, the test data was taken from a different set of 250 people than the original training data. Still group split between Census Bureau employees and high school students. This helps us to give us confidence that our system can recognize digits from people whose writing it didn't seem during training. We will use the notation X to denote a training input. It will be convenient to regard each training input X as 28 by 28. This is equal to 784 dimensional vector. Each entry in the vector represents the gray value of the single pixel in the image, and we will denote the corresponding desired output by y, which is a function of x, where is a 10-dimensional vector. For example, if a particular training image x depicts a 6, then yeah, they have a 1 at this vector here. And this desired output from the network. Note that T here is the transpose operation, turning a row vector into ordinary column. So you basically shift this vector here by 90 degrees. We would like what we did like as an algorithm, which lets us find weights and biases, so the input from the network approximates y function of x for all inputs x. To quantify how well we were achieving this goal, we define a cost function. So before I even do this, I'm actually just gonna write this network down, because it's important. So this is gonna take some time, but I will do this. I think this is 10 inputs, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and then we have, as a hidden layer, we have 5 other. And then we have another 10, I think. And actually, this is not the correct diagram or network. It is this one here. So we have, this is actually 1, 2, 3, 4, 5, 6, 7, 8. So I wrote this whole freaking network wrong. That's my bad. Yeah, because it's 8. No, it's not 8 times 8. Stupid. Is it 8 really? 1, 2, 3, 4, 5, 6, 8. It is. Okay. And then we have 15, I think. And then we have 10. Okay, and now we're gonna like draw all the freaking lines between this. This is gonna be Bruh. And super bad at drawing lines, by the way. But yeah, that's one. Oh gosh. Actually I have this one here. I can use this one here, actually. It's really good. Dude, it's even difficult to paint all of these networks. Jesus. Yeah, painting this is disgustingly difficult, but you know. Oh my god. I mean, it's gonna look pretty cool when I've completed like whole this whole network, but it's gonna take some time to write. Yeah, I will probably come back to this, but at least I know how it works now. I'm gonna do this later. So we did go through this math. We are here basically. So we would like this is an algorithm which lets us find weights and biases so that the output from the network approximates the function of x for all training inputs of x. To quantify how we are achieving this goal, we define the cost function. So we're gonna write this down. Cost function. So the input here is the weights and biases, and this is 100% equal to, because this means like this cost function is defined by this. There's one divided by n, and n is a set number of neurons, I think, if I'm not mistaken in here. And then we have the absolute value of the function of x, which is a delta function, and a, I'm not sure what it is at the moment, but I guess the w denotes the collection of all weights, so let's find that. Notes there. Weights, right? In the network, all right, in the network. Then B is all the biases. And then we have N, which is the total number of training inputs. Okay. Right, and then we have A, which is a vector of outputs from the network. All right. A is the vector of outputs from the network when X is input. Right. That makes sense. Right. Of course, the output A depends on X, W, and B, which makes sense. Otherwise, this would not be a function. But to keep the notation simple, I haven't explicitly indicated this dependence. The notation, which is 2 brackets, just denotes the usual length of the function for a vector. We will call C the quadratic cost function. So it's the quadratic cost function. Okay. All right. It's also sometimes known as the mean squared error. Okay. But why didn't they just say that? That would be a lot easier for me, because I have done statistical math before. Inspecting the form of the quadratic cost function, or the MSE, we see that it is non-negative, since every term in the sum is non-negative. Furthermore, the cost becomes small, then it's almost zero. So when the cost function, or no, is it the, since every term in the sum is non-negative, further, okay, that makes sense. It was okay, so if all of these terms goes to zero, we basically have something multiplied by zero, which is equal to zero. Like, that is not the most difficult thing to do, understand. Precisely when the y function is approximately equal to a for all training inputs x. Yeah, makes sense. So our training algorithm has done a good job if it can find weights and biases so that we are almost close to zero. By contrast, it's not doing so well when it's large. That would mean that the y function is not close to the output a for a large number of inputs, so the aim for our training algorithm will be to minimize the costs as a function of the weights and the biases. In other words, we want to find a set of weights and biases which makes the cost as small as possible, and we will do that by using an algorithm known as gradient descent. Now, okay, so this makes sense, because when you train an AI, you basically see two values repeatedly in the terminal, which is cost and accuracy. And cost you want to have as low as possible, and the cost for that they probably use is this quadratic cost function, which is the mean squared most, what is it called? I just forgot. Mean squared error, right? So yx is basically the input and a is the output. So when they are close together, you basically have the right function. Okay.